Here is where we are. We now know that state feedback is really powerful. It can give us arbitrary closed-loop eigenvalue placement. This is not just important for stability. If you can place the eigenvalues arbitrarily you want, you can get better tracking as well, not just a better stability. And then if the state is not directly available, now we have talked about the concept of I can design something called an observer that gives you an estimate of the state X that you can use for your feedback control. And that entire thing integrated together becomes an observer state feedback control. So that's the topic here. Today, I will talk about how we can design this observer to provide this estimate. And then next time we can spend a little bit more time on the whole closed loop system. So let's take a look at the observer first. If this is what we have, this is given to us, and our goal is to estimate X. So it seems natural if we know U, if we know the input, and we know A and B, then it seems natural to try, let's call this estimate as X hat. It seems natural to try this. So I just use a copy of the structure of the system and use the same input to drive the estimator. And observability design is similar to the controllability and stabilization design. What we need to be careful about is the stability of this estimator. So here you can immediately see that if A has some eigenvalues that are unstable, if the system itself is unstable, then running an unstable system like this in an open loop can be problematic in general. Right? So you have stability concerns, first of all. And then second is a general approach to design observers is to look at the arrows, aerodynamics. The aerodynamics means you look at how accurate you are between what you want to estimate and your estimator X. The dynamics of the arrow signal is how the arrow changes with respect to time. So it's E dot, which equals to X dot minus X hat dot. And it equals this minus this. So you get BU gets cancelled out. You're left with AX minus X hat. Or in other words, A times E. That is your aerodynamics. So you have a dynamic system, and then the initial condition is E0 equals to X0 minus X hat 0. X0 is whatever initial condition the system is. X hat 0 is your initial state estimate. Usually this is 0 if you don't have any idea about the system state. So E0 then usually is X0. So you have a system that has some initial conditions and then a aerodynamics that look like this. Immediately you see if system is unstable, if A has unstable eigenvalues, then the aerodynamics will be unstable. So this is not a particularly good design. Instead, this doesn't work so well. We try to use a similar structure, but we want to throw in some mechanism such that things doesn't go too crazy. So we throw in a correction term L and a correction term like this. This one makes sure that if your estimate is too off, such that your state estimate and then you have an output estimate, y is cx, and then y hat is c times x hat, you have the difference between your actual measurement, this is what you can measure, and your estimated output as a correction term. And then you have some gain to change how it influences the dynamics over here. Then things will become much different from this condition. Let's work out the details. Use exactly the same logic. We analyze the error. So plug in E dot, we calculate E dot, which equals to x dot minus x hat dot. Same story is ax plus bu minus x hat dot. So it's ax hat minus bu, and then minus L y minus y hat. Things cancel out for the input term. And then for here, we have the output is L times Cx minus Cx hat. That's how the output relates to the state. So you have x minus x hat, and you have x minus x hat. So you can combine things, and then in the end, you're going to have A that is the updated aerodynamics if you choose to include this correction term. And the way that this correction term gets into the picture actually is a little bit relatable to this. Here, state feedback control, you have a gain, and you have gain multiplied with, if you're stabilizing control, then x is ideally 0, right? If we want to stabilize the system, we want to drive the system to the origin. So this is sort of the signal that we want to keep to be small. And same story here. We have a gain, we have a term that we want to keep to small. When things happen in a perfect harmony, then we have x hat equal to x. Then this is 0 in the ideal case. So that's the basic concept. Let us now add the observability into the mathematics. Let's now look at, if the system is observable, how freely can we design the aerodynamics? More specifically, let's talk about when things are in the observable canonical form, how freely can we design this matrix? So in the observable canonical form, A is negative A2, negative A1, negative A0, 1, 0, 0. Let's say it's a 3 by 3 case. And then C is 1, 0, 0. Let's look at when things happen this way, what's going to look like in A minus LC. All right, let's work on the dimension first again. If C is this row vector, what is the dimension of L to make things work? N by 1, and then in our case, N is 3, so L should look like this. N by 1, one column, let's say L1, L2, L3. That's how you can make the dimension of the matrix work, matrix multiplication work. Now, A, we have the structure. So A minus LC is 0, negative A2, negative A1, negative A0. This time I'm going to write things in one step, the entire matrix out. So it's A minus LC. LC is going to be L1 0 0, L2 0 0, L3 0 0. That's L times C. So A minus LC therefore is going to be negative A2 minus L1, negative A1 minus L2, negative A0 minus L3. And then it doesn't change the other columns. So what do you see? I can arbitrarily, by choosing L1, L2, and L3, I can arbitrarily change all the coefficients in this new matrix. That means I can arbitrarily change the eigenvalues of this matrix. All right, so arbitrary I can arbitrarily change all the eigenvalues of this matrix that represents the dynamics of the error, the estimation error. So that means I can arbitrarily change how my error will converge. I can make it stable, I can make it to converge super fast, I can make it to converge slower. So this is the conclusion. We can have stable observer and arbitrary design of how fast the observer converges. So the conclusion, therefore, is if the system is observable, then we can design the observer gain to arbitrarily control my aerodynamics. I can arbitrarily make my estimator to be close to my actual state. And then same logic, this is if it's in observable canonical form. If it's not in observable canonical form, we can transform the system into observable canonical form. Okay, that is the basic concept of observer state feedback control. Now actually you have started to combine all the things together. What's going to come later is just now you do this, we introduce this concept to do this manually. There are ways to do this optimally. There are ways to design L and K to be in an optimal way so that you don't have to choose these eigenvalues by yourself. So there are automatic ways to design these.